In last lecture, we have covered our statements of second law of thermodynamics, and along with it, we have also discussed equivalence of Kelvin Planck and Clausius statements. In this lecture, we will start with Carnot cycle. Carnot cycle. So, Carnot cycle is defined as a reversible cycle. Carnot is a cycle is a reversible cycle. It is a cycle, and a cycle is said to be reversible when each process of the cycle is reversible. Okay, so you should remember this point. A cycle is said to be reversible cycle when each process in the cycle is reversible. Okay. So we will draw the Carnot cycle on PV diagram, and I will explain all the processes which are occurring. Okay, so let me draw it. So this is P axis, this is V axis. Okay, so you know from the previous discussion that the slope of adiabatic curve is greater than slope of isothermal curve on PV axis. So from here that thing will be used. Okay, so let me draw the diagram first. Okay, so this cycle is called Carnot cycle. Here, let me rename the points first. So let's say this is point 1, this is point 2, this is state 3 and state 4. Okay, these points are also called as states. Okay, so the system is first will move from 1 to 2, then 2 to 3, then 3 to 4, then 4 to 1. Okay, so these two the processes. Now I will describe each process. What does each process defines? Okay, so first I will discuss about process 1 to 2. So process 1 to 2 is reversible. Or we can or since all the processes are reversible, so I can directly write it as, so okay, let it write it as this: reversible isothermal heat addition. Okay, so the process is reversible isothermal heat addition. Next we will move to process 2-3. So process 2-3 is called reversible adiabatic expansion. expansion. Process 3 to 1 is called reversible isothermal heat rejection. And this is process 3 to 4, and then process 4 to 1 is known as reversible adiabatic compression. Okay, so from here we can see that for this Carnot cycle, in process 1 to 2 we supplied the heat Q to the system, Qs to the system, and in process 3 to 4 the heat Qr is rejected by the system. Okay, so this complete cycle is called Carnot cycle. Okay, so here two more things I would like to discuss. First is what is isothermal and adiabatic. Okay, so you know that isothermal process is at constant temperature. So at each and every point the system should attain equilibrium with the surrounding. Okay, so this isothermal process must be very slow. Okay, very slow. And on contrary to isothermal, the adiabatic process, for adiabatic we say that there is no heat interaction between system and surrounding. Okay, it means that this process should be very fast. Only if it very fast, then it won't have time to interact with the surrounding, and it can be considered reversible adiabatic. Okay, so the process 1 to 2 is reversible isothermal heat addition. Process 2 to 3 is reversible adiabatic expansion. There is expansion increase in volume. And process 3 to 1 is again isothermal process, but 3 to 4 again isothermal, but what happens in here that the system is rejecting some heat. Process 4 to 1, as you can see here, it is again reversible adiabatic compression. So the Carnot cycle consists of two adiabatic and two isothermal processes. Okay, so Carnot cycle consists of two isothermals and two adiabatic processes. So isothermal process is very slow, as I mentioned earlier, and this adiabatic process are very fast processes. So if we want to like combine these both things, like isothermal and adiabatic, very slow and very fast processes, so this is not feasible. Okay, so therefore the Carnot cycle is not a practical cycle, but it is this cycle is used for comparing other actual cycles. Okay, so you cannot create a cycle which in a process will be very fast, and in another process it will be very slow. Okay, so this is the Carnot cycle isn't a real cycle. It is only a theoretical cycle that we have made, which will have the highest efficiency, we can say. And we use this Carnot cycle to for the comparison of other actual cycles which are actually feasible. Okay, next we will discuss Carnot theorem. What is Carnot theorem? So the Carnot theorem says that for various engines operating between same temperature limits, so if there are various engines which are operating between same temperature limits, then no engine, we can say it that then no engine has efficiency greater than reversible cycle efficiency. Okay, so from this we can say that efficiency of an irreversible engine can never be more than the efficiency of reversible engine. Okay, when it is operating between the same temperature limit. From here we can say that, let's say this is the first point, eta irreversible is less than, always less than eta reversible. And when is it applicable? For same temperature limits. Okay, so there is second point, and the second point is for, okay, let me write it, efficiency of all reversible cycle or cycles operating between same temperature limits is same. So if there are more than one cycle, reversible cycle, which is operating between the same temperature limit, then all of their efficiencies will be same. Okay. Now for verification sake, let's say that we will consider, let me copy diagram here first. Okay, let's consider two engines between same temperature limit TH and TL. Let's say this is engine 1. This is our engine 1, which takes heat Q1 from higher source and releases heat Q2 at a lower source. And let's say this is a irreversible engine. Okay, so let me write it here, E irreversible. Okay, and let's say there is another engine which is reversible. Okay, reversible. So let's say work done W1 is provided by this, and or W irreversible, we can say W irreversible, and W reversible is the work provided by the reversible engine, which with same heat interactions with both the reservoirs. Okay, so let's assume that eta, that efficiency for irreversible cycle is greater than efficiency for reversible cycle. What does it mean? What is the efficiency of irreversible cycle? Irreversible cycle efficiency, I mean efficiency for any cycle desired effect upon input. Okay, so here desired effect is work done irreversible divided by Q1, and this should be greater than work done reversible divided by Q1. Okay, so from here we can get work done irreversible is greater than work done reversible. Now if we are saying that the work done for by the irreversible is greater than the work done by reversible. So we can apply this in again in, let's say, okay, let's wait a minute. Okay, so so assume this again. So let's say the heat engine is receiving heat Q1 from the higher source and releasing heat QL to the lower temperature source, and it will be making an output of work done irreversible. And this heat pump, let's consider it to be this heat engine is reversible and this heat pump is reversible. So we will provide the heat pump with the work done reversible. Okay, and for the same amount of heat that will be absorbed from the TL, we will reject heat Q1 to the higher temperature. So let's say that since this Q1 demand can be completed from here, okay, both of them can directly utilize the energy, so there is no need for the higher temperature source. Okay, and effectively this whole system will also produce a work will be work done irreversible minus work done reversible. Okay, so this will be the violation of Kelvin Planck statement. Okay, so we can say that we can reduce this diagram has been reduced as, if we consider that reversible efficiency is greater than irreversible efficiency is greater than reversible. So we can say that it has been reduced such that a system which is interacting with a single reservoir at a single temperature and has been continuously producing the work output. Okay, so this is itself is a violation of Kelvin Planck statement. So eta irreversible cannot be greater than eta reversible. Okay, we have verified this thing. Now we will move to next topic, and first before that we will discuss some important points with respect to reversible cycle. So for reversible cycle, so there are few points. Let's say first point is, actually I have already mentioned these points here, but I will just write it here. So efficiency of various reversible cycle between same temperature limit is same. The second point, okay, let me copy it here. Okay, the second point is eta for a reversible cycle is independent of working fluid. Okay, the third point is eta for a reversible cycle is the function of temperature only. Okay, so it will only depends on temperature limits, both higher and temperature limits. Okay, now we will be moving to our next topic, that will be, and when I say that the reversible efficiency is function of temperature, I mean the temperature of both the reservoirs TH and TL. Okay, now we will move to our next topic. Next topic is Clausius theorem, or Clausius inequality we also call it. Clausius inequality. Okay, so in case of Clausius equality, it is said that cyclic integration of del q by t is less than or equal to 0. That is, cyclic integration of del q by t is always less than or equal to 0 for all the practical possible cycles. Okay, so from here we get the values like three things. First is, if for a cycle, if del q by del t cyclic integration is less than 0, then the cycle is irreversible. Okay, if del q by del t of a cycle is equal to 0, then process is reversible. And the third is, if del q by del t is greater than 0, then cycle is impossible. Okay, so this Clausius inequality is for all practically possible cycles. Okay, next we will see we will study reversible and irreversible processes one by one. Okay, so let's say that first we have to we are considering reversible cycle. Okay, so case 1, that is reversible cycle. Okay, before we look into this, let me first tell you here something. Okay, let's remove this portion first. I will make a space for a new topic here, a little topic which will be of some importance in the next part. Okay, so I forgot to mention earlier about thermodynamic temperature scale. Okay, thermodynamic temperature scale. Okay, so I mentioned earlier in point number 3, for if cycle efficiency for a cycle is a function of t1 comma or we can say th comma tl. Okay, now this efficiency term is written as 1 minus QL by QH. Okay, we know this from let me show something. So let's see that this is a standard heat engine. Okay, so from here we can see that efficiency desired effect, 1 minus QL by QH, we can directly write it as here. Okay, so this will be equal to function of TH comma TL. So we can say from here that QL by QH can be written as 1 upon 1 minus function of TH minus TH comma TL. Okay, sorry, this QH minus QL. Okay, QH by QL. Okay, I think you get this point. Now this can be further written as function phi, let's say phi of TH comma TL. So now let's consider this cycle here. We will be using this cycle as example there. Okay, copy and from here we can write that using the same analogy we can write q1 by q2 is a function that is psi times of t1 comma t2. Similarly I can also write q2 by q3. Okay, q2 by q3 is equal to psi times of t2 comma t3. And similarly from combined equation I can write q1 by q3 is equal to psi of t1 comma t3. Okay, now next what I can do, I can write q1 by q2 as q1 by q3 upon q2 by q3. So this can be expressed as phi of t1 comma t3 upon phi of t2 comma t3. Now if we consider that our sink temperature is constant, okay, if the sink temperature is constant, so I can write it as in another function form, that is psi of t1 or upon psi of t2. Okay, so according to Kelvin we can consider this function psi to be equal to t. According to Kelvin we can take the psi of function t is equal to temperature. Okay, so we get from here q1 by q2 is equal to t1 by t2. So we can write efficiency is equal to 1 minus t2 by t1. Okay, this is also known as Carnot efficiency. Okay, so you should remember this relation. This will be useful in our further study, like here when I am showing it for reversible cycle. Okay, so consider reversible cycle, we will use this cycle only. Let's consider this cycle here. So if there is a reversible cycle, so in case of reversible cycle I can write cyclic integral del q by t as what are the, like let me first redefine this terms. Okay, let's say this is our delta qh is heat from higher source, delta ql is heat rejected to the low temperature source, and let's say that delta w is the work done produced by the heat engine. Okay, so we can write del q by cyclic integration of del q by t as del qh by, so if we consider this heat engine to be our system, then we can see that since this del qh heat is supplied to the system, we will take it as positive, and it is supplied at as a constant temperature of Th. Okay, so we will write it as Th, del QH upon Th. Okay, now this del Q2 del QL heat is rejected from the system. Okay, so we will take it as negative of del QL upon at a temperature of TL. Okay, so we get cyclic integration of del q by t as del qh by th minus del ql by tl. Now from our Kelvin scale which we studied earlier, if we consider, so this Kelvin scale was only like I have told earlier, this E2 when these engines are reversible only, then this was applicable, and from here only we can see that since this efficiency relation is for reversible cycle, so this whole thermodynamic temperature scale was only applicable for reversible cycle. So if we consider if cycle is irreversible, cycle is reversible, So what will happen if cycle is reversible? Then we can write del QH by del QL is equal to TH by TL. From here we can write del QH by del QL, del QH by TH is equal to del QL by TL. And if we substitute this equation here, we can get integral of del Q by T for a reversible cycle, for a reversible process, is equal to 0. So we have proven that for a reversible cycle, cyclic integration del Q by T is equal to 0. Now for case 2 we will consider, like in case 1 we considered reversible cycle, so for case 2 we will consider a irreversible cycle. Okay, case 2, that is irreversible cycle. Okay, so let's consider this cycle. Okay, instead of considering this, now there is one thing I missed to tell you, that since this del Q by del T cyclic integral is 0, so we can say that this term del Q by T is a property. Okay, so in further lecture, or in this lecture only, at last we will see that this term del Q by T is termed as entropy. Okay, and this entropy is a property of the system. Okay, so for irreversible cycle system we have considered this figure. Let's say that we have a reversible cycle and irreversible cycle. Okay, let's say this is E reversible, this is E irreversible. Okay, so this Q1 amount of heat is absorbed, and then Q2 is released here, and then work done produced by this reversible is work reversible, and similarly this heat engine also receives heat Q1 from here and rejects heat. So both of them will absorb the same amount of heat, but while rejecting, this irreversible engine will reject some another heat, let's say Q2 dash. Okay, and will produce work done, that is irreversible, work done irreversible. Okay, so as we have done earlier, we have considered eta irreversible to be greater than, not that, so we know that eta reversible is greater than eta irreversible. Okay, so from here we can write W1 by Q1 is greater than, W reversible by Q1 is greater than W irreversible by Q1. From here we can say that W reversible is greater than W irreversible. Okay, now using this relation and first law of thermodynamics, in both the cases we can get that Q2 dash is greater than Q2. It means that heat reacted in irreversible process is more than heat reacted in reversible process. Now we will apply the same cyclic integration of del Q by T for, let's say, our irreversible engine. Okay, so for irreversible engine, in case of if we apply for irreversible, we will get del Q by T is equal to Q1 heat is released at temperature TH, and Q2 dash heat is rejected at temperature TL. We will be doing this equation. Okay, now from this we can, now if we consider this reversible cycle, from reversible cycle we can write Q1 by TH is equal to Q2 by TL. So here we will use that to convert this Q1 by H into Q2 by TL minus Q2 dash by TL. So we can write it as 1 upon TL q2 minus q2 dash. From here we know that q2 dash is greater than value of q2, so this term will always be less than 0. Okay, if we use this equation, so this term will always be less than 0. So from here we can say that for irreversible cycle, cyclic integration del q by t is always less than 0. Okay, I hope you guys understood it well. Okay, now we will be moving to our next topic. So before that, but let me clarify a few things here. As I mentioned earlier, efficiency is written as efficiency of system is written as 1 minus q2 by, or we can write it as ql by qh, or q2 by q1, let's say, according to this diagram only we are writing. Okay, so for this relation is applicable for both reversible and irreversible. Okay, but for reversible, if we consider reversible heat exchanger, heat engine, we can say that efficiency reversible can be written as 1 minus from that Kelvin temperature scale. We know that q2 by q1 can be written as t2 by t1. So for reversible, I can write eta reversible is equal to 1 minus t2 by t1, or 1 minus tl by th. Okay, now this efficiency is also the maximum efficiency possible. Okay, and also called Kelvin Carnot efficiency. Okay, and this temperature T, all the temperature T here are in Kelvin. T in Kelvin, all the temperatures are taken is in Kelvin. Okay, similarly we can also for refrigeration COP, I told you earlier that, let's say for refrigeration it is QL upon QH minus QL. So we can also transfer in terms of temperature this, and that will be for reversible. So COP of refrigeration, and this in case of reversible can be written as TL upon TH minus TL. Okay, similarly we can also write for heat pump, but this COP of refrigeration is the maximum possible value of COP in case of refrigeration. Okay, similarly we can also calculate the value of COP for reversible heat pump, which will be TH upon TH minus TL. Okay, now we will be moving to our next topic. So our next topic is entropy. Okay, so today we will start entropy. Okay, so we will start entropy from here. So entropy, for study of entropy, we will study is two cases like we studied earlier. Okay, so first case is reversible. Case 1, reversible cycle, and the case 2 is irreversible. Irreversible cycle. Okay, now for both we will draw a PV diagram. Okay, so let's draw PV diagram. Let's consider process from point 1 to point 2, and there are three processes. Okay, let's say it point process A, this is turn process B, and this is another process C, and all these three processes are irreversible. Okay, and in case of irreversible, we will take the same diagram. The only difference is the process C, there will be irreversible. Okay, so this process C, okay, so this here is an irreversible process. Okay, This C is irreversible, and but both processes A and B are reversible. Okay. Now what we will do, we will apply the same del q by d cyclic integration of del q by t, but for reversible process we know that its value is 0. It means that delta q by t in process 1a2 1a2 plus delta q by t in process 2b1 equal to 0, and here we have considered like cycle 1. This is for cycle 1a 2b1. Okay. Now for other cycle, let's say other cycle to be 1a 2c1. Okay. So here we will get del q by t at 1a2 plus del q by t for 2c1 will get 0 this term also, because all the processes are reversible. Okay. Now from these two we can subtract the both equations. So on subtracting both equation, let's subtract it. So this both terms will cancel out. Okay. And we will get del q at t at from process 2b1 will be equal to del q by t from process 2c1. And since process 2b1 and 2c1 both are reversible and in same direction, that is from 2 to 1, so from here we can say that this term del q by t is a property. Okay. And this term del q by t, which is property, is also known to be the quantity del q by t that is evaluated here is called entropy. Okay. It's called entropy, and entropy is a property. So we can directly write it as ds is equal to del q by t in case of reversible processes. Reversible. So this is a point to be remembered. Next, while discussing for irreversible cycle, so for irreversible cycle we know that cyclic integration of del q by t for irreversible is less than 0. Okay. So we will again consider both the paths 1a2 b1 and 1a2 c1. Okay. But now since process 1a2 b1 is reversible process, so this will del q by t will be equal to 0. Del q by t is equal to 0. Okay. And from here we can write del q by t from 1a2 is equal to minus of or plus del q by t from 2b1 is equal to 0. And if we talk about process 1a2 c1, so for this we can use this relation. Okay. And from here we can write del q by t from 1a2 plus del q by t from 2c1 must be less than 0. And if we use this equation here, so we can get del q by t from 1a2 will be del q by minus times of del q by t from 2b1 plus del q by t from 2c1 equal to 0, so less than 0. So from here we can say that del q by t for 2c1 is greater than del q by t for 2b1. Now this process 2c1 is irreversible, So from here we can also say del q by t for irreversible is greater than del q by t for reversible, since process 2b1 is reversible. From here we get the value, that is okay, so this del q by t at reversible is also termed as ds. Okay, so okay, sorry, this sign should be like this. Okay, and hence we can write from here that ds is always greater than del q by del t at for irreversible. Okay, now if we combine both of these equations, this equation and this equation, we get ds to be greater than equal to del q by t. Okay, this is a very important formula. So change in entropy is always greater than equal to del q by t. Okay, for the irreversible process we can further proceed it, let's say like ds is equal to, so since ds value is greater than, so something must be added on side of del q by t such that the value should be equal. So this value is as generation plus del q by t. Okay, so here we see that this del q by t value calculated from irreversible path generally comes less, del q by t calculated from irreversible path is less than del q by t from reversible path. So there must be some extra entropy that is generated in case of irreversibility, and that entropy generation is entropy generated is called entropy generation, and it is generally generated in all the irreversible cases. So for irreversible case, ds is written as S generation plus del q by t for irreversible cycle. Okay, and as I have already told you that entropy is a property, but property generation is not a property. Okay, so this is a property, but this S generation is not a property. Okay, this ds is a property, this is not a property. Okay, and this entropy generation is specifically represent, what does it represent? It represents the degradation of energy So our henceforth our second law of thermodynamics is also known as law of degradation of energy, because due to presence of irreversibility our energy is degraded. Okay, from here we will discuss what is the significance of entropy. Okay, so first you should feel what is entropy. Okay, so entropy, definition of entropy includes it tells us that entropy is a measure of disorder or randomness. Okay, so it's okay that entropy is a measure of disorder or randomness, but how it is how it is significant in our study. Okay, so this entropy tells us many things. So let's say this entropy is significant to measure irreversibility. Okay, so we know that entropy increases in a irreversible process. Okay, we know that del q ds is always greater than del q by t. So for any irreversible process, the entropy increases. Okay, because irreversible processes also include friction, mixing, and unrestrained expansion. If you talk about reversible process, for reversible process, the entropy remain constant. Okay, and entropy also gives us the direction of heat flow. Okay, so naturally heat flows from hot end to cold end. So entropy tell us which direction the heat will flow. Next, it also tells us the entropy also tells us the direction of process. We also use entropy to tell direction of a process. So entropy helps us determine whether a process is spontaneous or not. Okay, a process can occur spontaneously only when if its total entropy increases. Okay, so delta S must be greater than 0 for spontaneous process. Okay, next topic, entropy tells us about entropy limits engine efficiency. So we know that ideally what should be the engine efficiency. So we can tell that it should be 100%. But what happens due to the presence of entropy? 100% efficiency cannot be obtained. Okay, because there will also always be some friction present in the system and something like this. So there is always be some entropy loss. The entropy of the system will keep on increase. Even the reversible system provides some particular amount of entropy, that is amount of ds is equal to del q by t. So that amount of entropy will always be available in the system. Okay, so energy cannot be efficiency of the heat engine cannot be 100%. Okay, now let's say one more thing. Since I've said earlier that entropy is a measure of disorder or randomness. So for if we talk about entropy, then the higher the entropy, the more disordered the system will be. Okay, now I think you should get the basic gist of the term entropy. So more randomness is present, higher the entropy of the system will be. The less randomness, less entropy of the system. Okay, now we will start entropy analysis. Let's start with entropy analysis. Entropy analysis. Okay, so there are three type of entropy analysis that we will that can be done. First is heat transfer. Second is mass transfer. Third is entropy generation. Okay, so this heat transfer and mass transfer both are external interaction type. Okay, and this entropy generation is a internal interaction. Because entropy generation can occur due to our irreversibility of the system. Okay, now if we talk about same amount of energy, let's talk about the same amount of energy. In case of same amount of energy, if temperature of the system is increased, then its entropy will decrease. Because if the energy amount is same at higher temperature, the grade will be high. If we only talk about the heat energy also, so heat at heat can be available at same amount of heat can be available at two temperatures, one at low temperature and second at high temperature. Okay, but the high temperature stored heat will have higher grade of energy. Okay, so if the temperature is high, then the randomness, or we can say that the disorder in the uh, molecules will be less. Okay, so the entropy will be less. And if we talk about the same amount of energy at a lower temperature, at lower temperature the randomness will be very high, so the entropy value will be very large. Okay, now there's another thing we can talk about. Like if we have same mass. Okay, if we take same mass, then on increasing temperature our energy of system will be increasing. Let's say there is a metal ball. If we increase the temperature of metal ball, our energy will increase, and so will our entropy of the system. Okay, next, if we decrease the temperature, we know that our energy of the system will decrease, and so will be the entropy. Okay, so from here we can say that if the same amount of heat, so let's see how this thing came to being. Okay, so we know that our ds, if we take the reversible system, can be written as delta q by t. Now let's say that amount of we will talk about this same amount of energy first. So let's say that if the amount of energy is same, okay, then our dq is constant. Okay, let's move it here. Okay, our dq is constant. Since dq is constant, if we increase the value of t, let's say that we increase the value of t, then we can see that our delta s, or we can directly use as s entropy, so our entropy value will be decreasing. Okay, so we say that for the same amount of energy our entropy is decreasing. Okay, next, if we talk about if we like decrease the temperature, our entropy will increase. Next, if we talk about the same mass, let me draw it here also. So we can say that our entropy can be written as q by t. Okay, here we can also write it as q by t, this. Okay, now if we increase like, since the mass is same, we know that q, let's say q, if this for same mass we write q is equal to mc delta t. Okay, let's say if the mass is same, but we increase the temperature. On increasing the temperature, we know that while increasing the temperature, the q value will also increase. We can write it as mct, so q will be delta t only. Okay, now if we let's say that mathematical example of 1 by 2, what is value of 1 by 2? Value of 1 by 2 is 0.5. If we say it is 2 by 3, what is the value of 2 by 3? 0.66. Okay, so if we increase both values, both numerator and denominator, I would like tell the same amount. So we have increased numerator by 1 and denominator also by 1, so we so our value will increase. Okay, our answer will increase from 0.5 to we get to 0.667. Okay, similarly if we add both 1 in numerator and denominator, so we will get 0.75. Again there is increase in value. So let's say that we increase the temperature by 1 degrees. Okay, so we will increase q by 1 unit, and similarly we will also increase t by 1 unit. Okay, so our entropy value will also increase. And in similar way, if we decrease the value of t, our energy will decrease, and so will our entropy. I hope you understand this. Now there is two more points. If gas is scattered to the larger volume, okay. So if gas is scattered to larger volume, then what will happen? Then entropy of the gas will increase. Okay. Next point is, if total mass of system increases, if we increase the mass of system, from here we can see that if we increase the mass, our entropy will also increase. Okay. Now there is one more important point. Entropy uh, entropy of high grade energy equal to 0. Okay. So high grade energy, what is high grade energy? Like kinetic energy, potential energy, energy given system to the system, like in form of work given to the system, or work received from the system. These are all directional energy, and also called high grade energy. And the entropy associated with these high grade energy will be equal to 0, because there will be no randomness in the system due to the high grade energy presence. Okay. So let's say for this case we consider a piston cylinder arrangement. Okay, let's say this is the cylinder, is the piston, and the cylinder is filled with the some gas. Let's say that work is done on the system W on the gas, let's say. So what will happen? There are two things that will happen. The temperature of the gas will increase and volume of the gas will decrease. Okay, so due to increase in temperature, the entropy of the gas will also increase. Okay, but due to decrease in volume, entropy will decrease. Hence we can say that net entropy will still be 0. Okay. So we can say it from here that high grade energy associate energy entropy associated with the high grade energy is 0. Okay. So we will finish our lecture here today. In next lecture we will discuss fixed mass entropy analysis, and after that we will consider the entropy formula for various type of processes. So last lecture will be our final lecture on second law of thermodynamics.